今天比较冷哈，所以来的人比较少，是，还是今天还没到。Right. Good morning, ladies and gentlemen. So let's recap what we have learned on Wednesday. Wednesday mainly we learned the X-ray. And the X-ray, the wavelength of the X-ray is in the range of the 0.001 nanometer to 10 nanometer. So if the wavelength beyond this range is not X-ray. It might be, for example, if the wavelength is smaller than this, it will be regarded as gamma ray, right? Okay, if the wavelength is more than 10 nanometer, it's regarded as ultraviolet. Okay, so this is the X-ray also is regarded as electromagnetic radiation, right? It belongs to electromagnetic radiation. Okay, so how are we going to generate X-ray? Okay, it's in the old time is done by a gas discharge tube. Okay, you already learned what is gas discharge tube. And for the modern tube for generate X-ray, it looks like this. So you have a target. It can be metal, and at this moment, at this time, in the modern time, we use copper here. Okay, so this is the metal anode. It can be tungsten. Okay, it can be anything, any metal. Okay, and we have a hot hot cathode. Hot cathode is the place to generate electron beams. So you have a very hot cathode and generate electrons, and electrons shoot from the cathode to the anode. And due to the energy matter interaction, so here we will generate X-ray. Okay, so and because we need energetic electron beam, so we will apply a very high voltage here. It's about 30,000 to 35,000, for example, 35,000 volt. Okay, and because we don't want to have any interactions for the electron beam with the gas, so this has to be a very high vacuum in this environment, so that electron can shoot from cathode to the anode without any disruption. Okay, so this is the generation of the X-ray, and then after we generate X-ray, we will get an X-ray spectrum. Okay, X-ray spectrum looks like this, containing two parts. The first part is called characteristic X-ray. That's what we already learned, right? K alpha, K beta, you know, L alpha, L beta is somewhere around here. Okay, so this is called characteristic X-ray. So all the metals has a different peaks in this range. Okay, for example, for the wavelength of the copper K alpha 1, the wavelength will be located in the 1.54 angstrom. So it's 1.54 angstrom is 1.54 angstrom somewhere here, right? Okay, so it's different for all the in this case, this is moly K alpha is here, right? So for the copper, K alpha is here. Okay, so this is the characteristic X-ray. However, as you can see, a well-shaped continuous wave, continuous peak, continuous curve is showing in these figures. This is called Brustronham continuum X-ray. Brustronham continuum X-ray is a kind of interaction. It's kind of inelastic interactions between the instant electron and the core of the atom, right? So you already learned this. and we follow Duham's law, we can find these the points here. Right. So this is the spectrum, X-ray spectrum. Okay. And finally, we talk about application of X-ray, and you already learned this. You have seen this before. We use this kind of application many times. If you go to the medical, if you go to the hospital, you have X-ray scanning your lung, right, for the health check. Or if you go to the airport, you have a security check, okay, or some kind of inspection for your luggage. So these applications. However, for the scientific application, is that if you don't know if you have unknown material, and you put the unknown material to a machine, and you will produce X-ray. For example, like EDX, WDS, XRF, this kind of machine can identify the material you use, okay, the unknown materials. But it's also only for the elements only. Okay, you know that it can be aluminum oxide, but the pink come out is aluminum. Okay, and oxygen. Right. Okay, so that's what we learned last week on Wednesday, and today after we finish the topic of the X-ray, today we are going to talk about X-ray diffraction. X-ray diffraction. So we use XRD here. There are two types of the X-ray diffraction. One is called Lowy diffraction, which is transmission of the X-ray through the objects, and you have a pattern on the opposite side of the X-ray. So this is called Lowy diffraction. Another one is called Braggs law or Braggs law diffraction. So this is reflection. It's not transmission. It's reflect. So X-ray bounce back from the surface of the object, and you will have constructive interference and or destructive interference. Okay, so we are going to talk about these two topics today. Right. So first of all, let's think what is diffraction. I'm sure you have this kind of experiment in your high school or at home. You can do the same experiment. So if what is the definition of the diffraction? The diffraction is the phenomenon of inhibited by the wave front. This is wave front, right? Wave front that passing the edge of the opaque body. This is called opaque body, right? Opaque body are modulated, thereby causing a redistribution of the energy. So this front actually is energy, okay, with the front. So when you have a slit here, and the wave front goes through from the left hand side to the right hand side, so you can see this this video, and then you have interference, okay, and then you have diffraction. So this is a very important information to talk about the matter which has wave behavior, okay. So if we know the diffraction, then what's X-ray diffraction? If you want to prove the X-ray has a phenomena of the diffraction, and you need to do experiment, okay. So X-ray diffraction is that this is the a metal, for example. A metal has atoms. Between atoms there is a d-spacing, the space between the atoms, right? That's why we call d-spacing. And you have X-ray. For example, this X-ray is from copper. Okay, the copper K alpha 1 is 1.54 angstrom. So if you go to dentist to check your teeth, and then they also use X-ray. The X-ray, this is the X-ray, the wavelength of an X-ray. Okay, so X-ray pass through this object which has a d-spacing here. As you can see, there's a space between the atoms. And if X-ray behave like a wave, so you can have a wave front. So you can have diffraction in this object. So this is what we know. When a beam of the X-ray imprints on a solid material, a portion of this beam will be scattered and in all directions, right? Scattered in all directions by the electrons associated with each atoms or ions that lies within the beam path. Okay, so the diffraction grating must have a space. So this is space, right? Comparable to the wave of the diffraction radiation. So you need to do this. What's the distance between the atoms, and what's the wavelength of the X-ray? So as you know, if you have a very big space between the atoms, the X-ray is very small. The wavelength of X-ray is very small. Diffraction is not going to happen. Okay, so if you narrow down the d-spacing between the atoms, or if you reduce the wavelength of the X-ray or of the electromagnetic radiation, then you will have this diffraction. So this distance and the wavelength of the X-ray need to be matched. It cannot to be too different. It cannot be too. It has to be very close. Okay. Right. So now let's take a look at the transmission diffraction, which is called Lowy diffraction. So this is you have seen this before, right? Last week. Okay, this is X-ray source. We already know. You know how to produce X-ray, and this is called collimator. Collimator is to make the beam, because the X-ray go to all the directions, and you have to collimate this X-ray to make it straight. Or the X-ray go to the same direction. Okay, if the X-ray go to the same direction, it's like X-ray beam, right? The beam here. Okay, so and because you have crystal materials here, a crystalline material means that all the atoms packed in a very good order. So you have a space between atoms. That's what we call d-spacing, or space, right? So by this kind of good packing, then you will have a pattern on the screen in another side of the X-ray. So you can find something like this. This is called pattern. Right. So this spots created by diffract X-rays. Okay. So why this happened? Because crystal is a regular three-dimensional lattice. So this is it behaves like a diffraction grating. Okay, diffraction grating. And the transmission X-ray will, if this material is not too thick, it's a film, a very thin, so X-ray can pass through this material, and then you will make a pattern like this. So spot patterns is imitative of the symmetry of the atomic arrangements. So this is what we call Lowy spots. So if you have different if you have different material put into this place, and you will get different pattern. Even though if you have the same material and you twist or you change the position or twist an angle, this pattern will be changed. Because if this face is 1 1 1, you got pattern 1. If this is 2 1 0, for example, if this plane is 2 1 0, you got different pattern B. Okay, so this X-ray diffraction tell you two informations, that different materials give you different pattern. Okay, different plane of the same material give you different pattern. Okay, so let's take a look at if we have the same material, and then this is a rotational symmetry we call fold. So assume we have a BCC, we have a material, we have a unit cell like this, the same one. Okay, so X-ray shoot from this direction. X-ray beam go to this direction. Okay, and you got a pattern like this. Okay, so for example, this plane is we call 100. This plane is 100, right? 100. Okay, so this is called rotational center. Okay, you have a center here, and you start to rotate. Okay, when you start to rotate 45 degree and 90 degree, when you rotate for a 90 degree, you realize after you rotate 90 degree, this is the same as this. The shape of this is same as this. Okay, that means what? That means if you shoot from this direction, if you rotate 90 degree, the pattern will be the same. Okay, and you realize if you rotate this pattern for 90 degree and pattern tell you it looks the same, the pattern looks the same, that means what? That means this phase, this plane is 100. Okay? Right, so we are talking, so this plane is 100, right? Okay? And then the fold is, the definition of fold is 360 degree divided by the base angle of rotation. So the base angle of rotation is, this is called base angle of rotation. If you rotate 90 degree, and this you will have for a plane 100, this you will call 4 folds. 4 fold. Okay, 90 degree. Right. How about 110? 110 is this one, right? 110. So 110 is this one, this plane. So it's not it looks like this, right? You have different x length of the x-axis and y-axis, because 110 is this one. So if the electron beam shoot from this direction, and then you got another pattern. Okay, now is pattern, right? Now is diffraction pattern. So what's the fold here? So if you rotate 90 degree, this is 90 degree, right? It doesn't show you the same pattern. But if you rotate 180 degree, the pattern will be the same. So how many folds is this 110 plane? How many folds? 2 folds, because 360 divided by 180. So it's 2 fold. So once you have 2 fold, you realize, wow, this plane is 110. It's now 100. Okay? Simple. Okay, how about this triangle? Triangle is this one, right? 111. So 111 here. So 111 here, again, you have a rotational center. When you start to rotate, how many degrees you rotate and you got the same pattern? How many? Well, what's the degree you rotate and you will get same pattern? 120, right? 120, right? If you rotate, use your imagination, 120. So if you 660 divided by 120, that will be 3 folds. So this is what we call 3-fold symmetry. Okay, so even though we don't know what the material is this, but we will know if this pattern rotate, and if this is 2-fold, right? If this is 2-fold, we know this is 110 plane. If this is 3-fold symmetry, we will know this is 111 plane. Okay, if this is 4-fold, this will be called 100 plane. Okay? Right. And this is the things you need to remember. If I tell you what the Lowy pattern diffraction pattern has a show you there's a 4 folds of the Lowy pattern. What's the planes of the crystal? Is the plane that electron beam shoot, or electron beam get the diffraction. Okay. Right. So this is another thing. Is if I ask you how many folds is this? So it just start to rotate, right? Rotate and then tell you that how many folds. Okay, for this cartoon, it's only one fold. For this one, this is 5 fold symmetry. Okay, right. So line diffraction pattern, as I told you, that 4 fold is 90 degree, 3 folds 120, 2 folds 180. Represent this one. So this is 4 fold, 3 fold, 2 fold. Okay. So this is 100 plane, and this is 111 plane, and this is 100 plane. So this is very useful tool, right? If you have an X-ray beam, if you have a machine which has an X-ray beam and you have object, you put the object into the X-ray beam, X-ray machine, you can realize what's the plane you are looking at. So line diffraction is used to measure the crystal orientation, right? Crystal orientation like 11110. The numbers and arrangement of these spots depends on the type of the crystal and on its orientation related to the beam. Okay, so line patterns contain information on the symmetry of a crystal. However, it's impossible without additional data to establish unequivocally to which of the 23 crystal groups of the crystal belongs. So here we just know the plane, right? But we don't know what is this, because it really depends on distance, right? This spot and this spot, this spot and this spot. What's the distance? So you need more information to identify what is this. Okay. So this is some example of Lowy patterns. This is Lowy pattern of the silicon 110 planes. Okay, and this pattern, there are two things combined together. So we call superimposed electron beams patterns from the polycrystalline zinc and chromium. You see that there are some spots here. So this behavior, this is represent one thing, and there's a ring here. You might say, well, Professor, you just told me spots. You never talk about rings here. The rings normally represent polycrystalline. The spots represent single crystal. Okay. Okay. So if you have not a single crystal, if you have a polycrystal, that means you have many small particles, many small single crystal grams get together, and this is powder samples. You put the powder samples in X-ray diffraction machine, you will get something like this. We call Debye Scherer camera, and we got a ring like this. Because this, a polycrystal is regarded as a many small grams together, and then it's isotropic, right? It's not anisotropic. We just learned this. Right? We regard all the object of polycrystal as an anisotropic behavior or anisotropic properties. So this one, it looks like you have all the planes show you, all the small grams show you different angle, and that's why you have all the directions. Okay, that's equivalent, but this is 111, and this is 110, for example. So if electron beam shoot from this way, and you won't get a very good spots pattern. Instead, you will get a ring, something like this. Okay, a sample of the hundreds of the crystal, like a powder samples, okay, shows that the diffraction beams formed continuous combs. Okay, a circle of the film is used to record. This is the film to record, right? To record the diffraction patterns as shown. Each cones intercept the films given the diffraction lines, right? The diffraction lines. The lines are seems as an arc on the film. This is the arc, right? So this is a polycrystalline. Right. So Lowy, he found this actually. He want to prove that the X-ray is behave like a wave. Okay. And then these two gentlemen prove his idea, Lowry's idea, by using this crystal. And this is the pattern they found. Okay, he got Nobel Prize. Okay, this demonstrates that the X-ray could be described as a wave. Everything has a diffraction behavior. We can regard the object or the things as a wave, right? Right. This you know. Anyway, they are great. Right. Right. Okay. So now let's think of the another topic, which is refraction and diffraction of the pattern. So this we are going to introduce you Braggs law. Instead of shooting the electron beams through the object, if this object is very big and very thick, the X-ray cannot pass through that well. So instead of transmission, we have refraction and diffraction pattern. Okay, especially this is what we call refraction pattern. So before we talk about this, let's recap the interference. So what is interference of the thing of the wave? So if I have two waves which has the same parallel wave goes through this from left to the right, okay, and then they have the same attitude and then they have the same path. So this looks like laser, right? Laser. Anyway, so for some reason there's a scattering event. So it makes the wave change the attitude or change the frequency. Okay, for some reason. Okay, so you don't know, but after that they come out like it's the same thing. This is wave plan 1 and wave plan 2. And if they behave the same thing, that means what? That means this is called constructive interference. If you have constructive interference, the attitude will be higher, right? From A to 2A. That means what we call interference. Okay, how about destructive interference? Destructive interference is that for some reason there's a scattering event and then they behave different. They behave differently. So this A was positive and this A was positive, it become negative. So you have what? You have interference. Okay, that's what we call destructive interference. So you got nothing from the outcome. This is income, right? Input, and this is output. Input, output. This output has a very good wave behavior, but this output has nothing. This is called destructive interference. And nowadays you have earphone. Remember in the first lecture of our course that we discussed about your earphone, right? There's kind of smart earphone. The smart earphone will have destructive interference with the sound from outside, with a special low frequency sound, and you produce another wave to make the destructive interference. That's why you hear nothing from the outside, especially low the sound of the low frequency sound, right? Sound. Right. So the diffraction of X-rays by a plane of atom is like this. So this is plane A, which is on the surface. The plane B of the atom is in the second layer. The third layer, plane C. So you have a X-ray shoot from this angle, right? This is called incident beams. Okay, this is atom. Atom here, atom A, atom B, layer A, layer B, and this is X-ray. So there's three information of this X-ray. The first one is it needs to be coherent. Okay, in a phase radiation. Coherent. So this is coherent, right? Second is a monochromatic. Monochromatic means you have exactly the same wavelength. Same wavelength. Right? Same wavelength. The third is that it needs to be parallel. This beam needs to be parallel. One of the important case is you use laser, right? Laser. Okay, so laser and go through this one, and this is the atoms on the surface. Okay, and if you have parallel X-ray go through this direction, and you will have refraction, right? Refraction here, and it can be constructive interference. It can be destructive interference. Okay, so where are we? Okay, and then this is a theta. You can change the angle, right? You can change the angle. So, and this is D spacing. And you remember that D is DHKL is equal to A divided by root H2, H power 2 plus K power 2 K plus L power 2. Remember, HKL represent what? Represent the plane, right? Hope you still remember. So let's take a look of the case 1, constructive interference. Okay, if this is a constructive interference, what happened? So the difference of the path length is, if you have constructive interference, the differences between these two beams is only the difference of the path length, which is this one and this one, with SQ here and QT here. Okay, so and then you know the angle, and if this is constructive interference, this is the angle here. So you understand, if this is constructive interference, it need to be the integer number with the wavelength, right? That's why you can have interference, constructive interference, and this lambda n integer number times wavelength equal to this one, right? Equal to this one. And how do you find out the path length of the SQ and the path length of the QT? Because you have an angle here and you have D spacing here. So D cosine, right? D cosine, you will know the SQ will be D sine. I'm sorry, D sine, right? This is sine. D sine. Yeah, this D sine theta and then plus D sine theta. This is another one, D sine theta. Okay, that will be, and in the end, the n lambda will be equal to 2D sine theta. So you got a very high intensity diffraction beam here, if this is a constructive interference. So ladies and gentlemen, I want you to remember n lambda equal to 2D sine theta. Easy, right? You need to remember this. Very likely this will be in your midterm exam, final exam paper. Okay, remember this? So all the information you need to know is what's the wavelength of this X-ray. So what is the D spacing between the atoms in the plane A and atoms in the plane B? Then what's the incident angle? Incident angle here, theta here. So there are three informations. If you got one of these three, if you got two of these three, you can find another one, right? Right, please remember this. So Braggs law, this is what we call Braggs law. The Braggs law is this one. The n can be is an integer number, can be 1, 2, 3, 4. But basically, normally we use 1. So, in order to understand, in order to find out this spacing, all you know is what? Lambda, the wavelength, because you can control this. You can, because if you use copper, that will be 1.5, right? 1.5 angstrom. And because this is the beam, the angle of the beam, so this is also easy for you to control. So once you know wavelength and theta, you will understand that this. You can obtain the D spacing through this Braggs law. Okay. Right. So if you know the block, if you know the D spacing, and I want you to find out the edge length, can you do that for me? Yes, you can. Why? Let me show you. So once you know the n lambda equal to 2d sine theta, right? So obtain the edge length from the D spacing. How? Because D is the interplanar spacing, right? D is the interplanar spacing. You know that, and you know the K, H, K, L. So if we are talking about a cubic crystal structure, which is the length of A equal to the length of B equal to the length of C, and then this is one. If you know this and you know this, of course you know this. Okay, vice versa. If you know this, and you will know this, right? If you know this, and you will know this. So for example, if we know this D is 1, 1, 0, and you put a D here, and you will know the A. Okay? Right. So again, this is also the fingerprints of the crystal, because all the different crystals got different D spacing, right? And you can have the different shooting angle, X-ray beam, right? Okay. So if you put this in, if you have X-ray for this crystal, X-ray for this crystal, of course the pattern you will get is different. So interference of the criteria plus the crystal structure D, BCC, and plane, you got a set of the expected refraction. Okay, and if you got a set of the expected refraction, this is the fingerprint of the crystal. Okay, so for the Lowy diffraction pattern or X-ray diffraction pattern or Bloch's law, you can also identify the unknown material, and also you can identify the plane of the material. Okay, so let me summarize here for you. X-rays of the to determine the crystal structure. You have income X-ray, you have outcome X-ray, outgoing X-ray, right? And you have detector. You can detect this is interference, interaction, or destructive interference. Okay, you have spacing here. Okay, and you understand the difference of the path, the length, the path length differences of the path length is only here. So, and this is D is equal to n lambda divided by 2 sine theta. Okay, so if you have a detector here and you have a theta here, this is the plot. The plot is theta is here, in the x-axis theta here, and then X-ray intensity from detector. So you want to know if it's constructive interference, and this is theta C here. So you will get a peak in this pattern, especially in this angle, right? And if you change your angle, you'll get another peak if this is constructive interference. Of course, you got nothing if this is a destructive interference, right? So the non-constructive interference is that if the Bloch's law is not satisfied, then the interference will be non-constructive in nature, so as to yield a very low intensity diffractive beam. So you got nothing, right? You got nothing. Nothing here. If this is destructive interference. Okay? No peak. Right. However, just now we are talking about a very simple case, which is a simple cubic structure. But if you have a BCC or FCC, sorry, this is FCC, this is BCC, it's a little bit more complicated. Okay? So for the Bloch's law, n lambda equal to 2d sine theta is only for the unit cells having the atoms are positioned at the cell corners. Simple cubic, right? So Box's law is a necessary but is not sufficient condition for the destructive by real crystal. Right. So here Box's law just tell you a very simple concept: constructive, destructive interference, and you got a pattern. But in the real life, this is more complicated because you have different type of the structure and you have different size of the atoms. Okay, you might have two type of the atoms in a crystal, right? So the next result should be presented with the consideration of the specific crystal structure. So it's too complicated, it's out of scope in our lecture, in our course, but you can find this in the database. So Box, he got Nobel Prize. He got Nobel Prize together with his father. How wonderful, right? Father and son got Nobel Prize together, and actually he's the youngest Nobel Prize winner. When he got a Nobel Prize winner, he's age of 25. Very young. Okay, thanks to his father, right? Without his father, I don't think he can get Nobel Prize so young. But anyway, I don't know. Forget about what I say. Right, but he's the youngest scientist, okay, or the youngest Nobel Prize winner in physics. The youngest in the world is age of 17. He won a Nobel Prize, Nobel Peace Prize. Okay, a girl, anyway, from Pakistan. Right. So here I want to show you that the diffraction technique we call XRD machine. XRD machine is a very important and powerful machine nowadays for us to use. Of course, expensive. If you want to have a very good X-ray diffraction machine, it's very expensive. Right. So how does it work? So this is X-ray. We call X-ray diffractometer. So first, of course, we obey the equation of n lambda equal to 2d sine theta. Okay, and then T is the X-ray source. You know, X-ray tube here. You already learned this X-ray. So we produce X-ray beam and shoot from the right to the left. Okay, S is a specimen. So you put a specimen here. You might say, wow, Professor, will you dropped? Of course it will drop. Why don't you put a cover, okay, on the top? But you can put it on the top. You can turn it around, right? But it's okay, just let you know this. Right, and then you have detector. You have detector here. So you have X-ray beam, you have specimen here, you have detector. And because this is theta, right? And detector here will be 2 theta. 2 theta here. Okay, so this is detector. And then O is the one is around specimen and detector rotate. This will rotate. Okay, in order to get all the directions of the orientation for the crystal, for the polycrystal, or for the powder specimens, right? And this detector will move. So of course X-ray doesn't move, and then this move. Okay, so you have angle theta and 2 theta here. So for this one, if the collector or detector stay here, you will get a peak, right? Okay, so if I move, and you might get nothing. If you move a theta here, you might get nothing. I should say 2 theta here, I'm sorry. This here will be 2 theta. 2 theta. Okay, 2 theta here. And then if you move, you got nothing, there is no peak. But if you move a little bit forward, you might get another peak too. You might get another peak come out. Okay, that's why you can get a set of the peaks and represent this type of crystal. This pattern represents this crystal, or this polycrystal, or this powder specimens. Okay, so the specimen, the powder or polycrystalline grain, and in the form of the flat plate. So this is random orientations ensure that the sum of the particles are properly orientated. Okay, every possible set of the crystallographic planes will be available for diffraction, right? So this rotate and you pack randomly. So you got something like this, and this is X-ray is monochromatic X-ray refraction, and then X-ray shoot from this side, and then you got a correction from this side. So this is a counter this C move, right? Constant angular velocities and record. So theta is half the angle. So as I just show you, you got a theta here, right? And you move, you got nothing, and then if you move, you got another pattern. So this one move, and it's got a set of patterns. A set of peaks. So this pattern can represent this material. Right, so let me see that. I think everybody is, we need to refresh ourselves, right? Okay, I think I better stop here. Let's play Kahoot first, and then we move on after Kahoot. So today the Kahoot is X-ray. X-ray. That's what we learned on Wednesday, right? You have 1 minute. Let's make it louder to wake up everybody.我们上课的东西都放在 YouTube 上面啦，哦，然后大家可以上去看，然后我把去年的也放上来了，所以你可以看下个礼拜我要教的东西，哦，让我变成 YouTuber 吧，好不好？让我变得很人气，好吧？开玩笑哈，最主要上网放的东西是要你先去学哦。如果你觉得我的英文对你来讲不够好，哦，你听不懂，哦，没关系，你可以上网看，哦，那它会有 subtitle， 对不对？会有 subtitle， 它可以用中文，哦，可以用日文，对，可以用英文 ，it's up to you， 哦，韩文，对不对？有个学生学韩文，因为他追韩星，哦，很厉害，对不对？哦，为了韩国的那些年轻的这个小鲜肉，哦，我的这个研究生为了追小鲜肉去学韩文，好厉害！我从来没有想象过我会学日文，因为是这个日本的这个女优，对不对？哦。不过我学日文是为了去日本，对，我去日本之前我完全日文都不会哦。那我太太是日本人，所以我一定要学日文，对不对？才能追到她嘛，对。才能骗到他，对，啊，他已经被我骗来台湾20年了，真的很不好意思。好 ，Are we ready to play？ 不要跟他讲哦，他说他本来说10年之后就要回日本了，可现在已经在台湾待20年了。好 ，Are we ready to play？ Okay, so let's go. 有点难哦。应该还好吧。 Okay, good, good. The majority of you got the right answer. 这主要是第二，选项2比较难一点点吧。其实选项1、3、4都蛮简单的，对不对？哦，一定不对的嘛，对不对？好，所以那个一定拿掉。好，所以很高兴大家都没有人答错哈。然后3，我们刚才在讲上课一开始的时候，还记得吗？哦，如果你够聪明，你够小聪明的话，我们在上课的时候讲那些东西，基本上就是给你一些 hint 嘛，对不对？哦，如果你是 early bird， 对不对？你 early bird 大概会比较知道。好，那第四个其实第3、第四也没什么争议啊，对，第4也没什么争议。好，那就第二其实是什么呀？我特别写电子的数目在上面给你看，有没有？是不是钨的原子量比较高，然后铜的原子量比较低？那原子量高低就是代表电子的数目嘛，对不对？还有这个质子的数目嘛，对不对？好，所以你的钨的这个N1 应该会很低，对不对？所以 N1 很低的话呢，你的 wavelength 会怎么样？很小嘛，对不对？因为你被打出来，所以你的这个 wavelength 很小，你的 X-ray 会比较强，就是你的 X-ray wavelength 会比较小，是不是 ？OK， 好，所以呢，就是第二是，所以你最后会纠结在一般来讲会纠结在这个跟这个啦，哦，那最后呢知道2是对的，那就对了，哦，好吧 ？OK， 好 ，good， 再想一下哦，好 ，Let's see that who got the top 3 position. The number three go to 25038. Who's this? Okay, good. The number 2 goes to 25043. Okay. 怎么会有2个？好 ，Number 1是不是 ？Number 1 OK, 25009 是你的 OK, good, congratulations. Right, OK. Excuse me. Right, excuse me. Right, so this is important, so that I think I left it here. You know, if we have a powder lead, right, 铅粉, right, a powder lead, and we put powder lead here into the stage as a specimen, and we have X-ray shoot to this specimen, and then we have a collector here. So we will get a set of the peaks, and this is the pattern of the powder lead. Okay, so the diffraction beam intensity as a function of 2 theta. This is 2 theta here because it is 2 theta, right? Okay, and then where is that? Where are we? Okay, so this diffraction angle 2 theta, and then the high intensity peaks result when the Bloch's diffraction condition is satisfied by some set of crystallographic planes. Okay, so as a result, the powder lead, you have powder lead if you have a microscope, and you can see that there are many small powder, many small particles, and become this, look like this. So you put this kind of small particle here, you will get a set of the peaks, something like this. So, and for example, in a 2 angle, like say 33 here, you got a peak, and then 37 you got another peak. Okay, and then 52 you got another peak. So etc., something like this. Okay, and then of course you don't know what is this, and of course you don't know why Professor write 110 plane here. You don't know, but you got, if you have unknown things in here, and then you put this peak to, you collect all the data and then send this data to a computer. Computer will analyze this data and tell you, wow, this unknown material is lead, and this peak is 110 plane. This peak is 200 plane. So as you know, when you do the scanning, you have more 110 plane on the surface, right? Okay, the intensity represents the number, right? Intensity represents the number. You have more numbers of 111, less number of 200. So let's X-ray diffraction pattern. For example, you have a set of this, and you put an unknown material in a powder into this X-ray diffraction machine, and you got 3 peaks like this. And then this diffraction, and the computer will tell you, wow, this is diffraction pattern of the polycrystalline alpha iron. Alpha iron, as you know, this is BCC structure. The BCC structure, and then the computer tell you this peak is 110, which is this plane, right? So this iron is BCC is 414, right? 414. This 110 plane is this one. This peak represents this plane. Okay, and this is 200. 200 represents this plane. And this 211 represent this one, this plane. Okay. Right. So X-ray diffractometer looks like this. It can be very expensive. Depends on what kind of function you want for this machine. Okay. So you have a sample here. You have an X-ray. You have a detector, right? X-ray. And detector, your specimen. Okay, and it rotate something like this. So X-ray diffraction technique is that this is called XRD, which is very powerful and very useful machine tool. So it can be a quantitative and quantitative chemical identification. As I just told you, that qualitative means what? You can identify what is this material. Quantitative, how much is this plane, is this surface, right? And also crystallographic orientation. Okay, and also you can measure the crystal size and residual stresses. Okay, we haven't talked about this yet. I'm going to show you in the next lecture. Okay, I don't know. Probably we still have time. Right, so this electron diffraction, not only X-ray can produce diffraction pattern, but electron beam also can produce diffraction pattern. So this is electromagnetic radiation. This is what? This is electron. Okay, particle. And also not only for X-ray, not only for electron, but also so neutron beams also can make diffraction. So neutron particle has a behavior like particle behavior and also wave behavior. Right. So for the data analysis of the X-ray diffraction, as I just mentioned, we can identify the sample. Right. So when you get a set of the pattern like this, you can put this set of pattern and you can check this database. You can check this database and the computer will analyze this for you. Right. So determine the Bragg angles for the peaks. Use this equation, and once you got this, you know this is 311, right? And you can, you know this 311. You can, if you know the D here, because lambda you know, theta you know, you can calculate the D. And after you know the D, and then you know this D is here is 311, and then you can get A. So this is a very easy calculation. I hope you can do it in your final exam. So this is equation you need to remember, and Bragg's law. This one only. Easy. So, and we are going to talk about Scherer formulas for the peak to understand what's the size of the grain. in the powdered sample. Okay, here is the example. Okay, this find D spacing and A. So if we have a plane 111 plane and the lattice constant A of the gold, so this is the gold and this is the pattern of the gold, which is you have 111 peak in like say 38 degree. You have a peak of 200 at 45 degree, and this is 111. I want you to find out 111. This is 111. This is gold, right? And this is 111 planes. So 111 here. So how can you do that for me? Can you do this for me? So if you say that, well, this is a 38.3 degree, then use this equation, right? You can find out the D first, and we regard as a 1 here, and lambda, you know, the lambda of the X-ray. Normally we use copper, so the wavelength of the copper K alpha 1, it will be 1.54 angstrom divided by 2 theta, 2 sine theta. Here is that the wavelength of a copper K alpha 1 will be 1.54, right? And then you put this number here. Okay, and you know the theta 38.3, right? So you put the numbers here, lambda and the 38.3. You got this. Well, there's one thing you need to be careful is that this theta is the Bloch's law theta. So this theta is 2 theta, right? This theta is 2 theta. So 38.3 need to divide it by 2. Okay. So as a result, use your calculator and you can find out D111 is 2.35 angstrom. Okay, and once you find out D spacing, and then if you know the relationship between the A and D, then you can find out A, right? How do you find out A? I need to tell you this is what kind of structure, BCC or FCC, and you can find out the relationship between D and A. Or you can use this equation, right? 111 and then 111 here, and you find out A here. Okay. Right. So this is a very basic calculation. However, for a complicated calculation, it's not like this. This example is in your textbook, but I don't think I want to show you how to do the calculation. It's a little bit complicated for BCC and FCC. So just let you know only. So X-ray pattern of a silica. If we have as you remember, I told you for the Lowy pattern, there's a ring and there's a spot in the pattern. So it's a combination of the polycrystal and single crystal, right? So in the Lowy pattern. So however, for the X-ray diffraction pattern, we also can have a combination of the peaks together. So this page shows you an example of a mixture of the silica. Do you know what is silica? Silica is SiO2. If this is amorphous silica, we regard amorphous silica as a glass body, right? If this is a crystal silica, we regard the silica as a single crystal, and which is 石英, right? Okay, so this is amorphous silica, SiO2. This single crystal, this the crystalline silica, SiO2. Okay, so for this one, so the red ball represents oxygen, the gray ball represents silica. So there are 3 forms of the silica, the three forms of the SiO2, which is amorphous silica and quartz, and this is crystal ball light. or another type of the structure for SiO2. However, if you use X-ray for this material, you got pattern 1. If you got X-ray diffraction pattern for this, you got pattern 2. If you got X-ray diffraction pattern, this is pattern 3. So this is how it looks like. You got something like this. And then you need to tell which one is quartz, which one is crystal bolite. Which peak belong to this peak belong to this one, or this peak belong to this one. So we need to do X-ray diffraction for each of these, right? So for the quartz, this is the X-ray diffraction of quartz. So this peak is quartz, this peak is quartz, and this peak is crystal bolite. Okay, this peak is crystal bolite, and there's no peak. This is a kind of a bold curve. Is crystal. Is a polycrystal. It's a amorphous silicon dioxide, which is glass. You know, if this pack irregularly, there's no X-ray diffraction pattern. It makes sense to you, right? It makes sense. So there's no pattern. So if you combine these 3 peaks together, it looks like this. Okay? So mixture equal to this mixture of the pattern equal to the quartz, peak of the quartz, peaks of the crystal bolite, plus the peaks of the glass. Okay? Good. Right. Okay. What happened? So this is another example of the patterns of mixtures. This you got a pattern and you can identify this peak is for copper 101, this is copper 111, this is alumina dioxide. Alumina oxide. Okay. Another example is this one. This is gallium nitride. This is Indian gallium nitride. So this peak is combination of the gallium nitride and Indian gallium nitride. Okay. Right. And also X-ray, the pattern also will affect by the pressure. You know, if I have a heavy pressure, or the very heavy pressure, the packing of the atom will be changed. So the diffraction pattern will be also changed, right? Okay, this just give you an example that this material, the pattern of this material, X-ray pattern of this material will be changed because of pressure. This is under this ambient pressure, this an atmospheric pressure, right? And this is pressure which is 4.9 gigapascal, okay, which is very heavy, very huge pressure. Right. Okay. So next topic is how to determine the crystal size. You know, we put the powders of lead in the X-ray diffraction, and we use X-ray patterns. And according to X-ray pattern, we can realize what's the size of the X-ray, what's the crystal size of this powder. The Scheller, he found an equation to tell us this, and this is also important. I will show you. We are going to introduce this to you next week. Okay, we run out of our time today. So I think I better stop here. Right. So do you have any question for me? We still have 1 minute. You know? Okay. So good. So that's it for today.